pulled together a summary of what we've been talking about with the first and second derivatives. Here's a graph of y. And so let's just label some points here. If we call this the point A, and call this the point B, and C, D, E. I think that's good for right now. The first thing that we could look at, let's first look at y prime. So on y prime, we know that y prime is going to be less than 0 anytime my function is decreasing. So that's going to be from negative infinity up until a, from c to b. And y prime is going to be greater than 0 for the other values. Y prime is going to be greater than 0 when my function is increasing. So from a to c and e to infinity. What else can we know about y prime? Well, so here's the first thing that we know. Here's the second thing. Third thing, y prime is going to have a maximum at, well, it's going to have a maximum when we have a point of inflection right here. That's the steepest it's going to be in that local area. So at x equals b. And it's going to have a minimum right there. So that's, steeper, 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 steeper. That's the steepest point, and then it gets shallower and shallower. So y prime is going to have a min at x equals d. More on y prime. Y prime is going to be increasing. So it's going to be increasing everywhere I draw blue. So increasing, increasing up to there, and then increasing everywhere thereafter. So y prime is increasing for x from negative infinity until b, and from d to infinity. And it's decreasing in the red areas. So my slope is getting smaller and smaller there. So it's decreasing for x being between b and d. Okay, well, that's a lot for y prime. Now if we look at y double prime is going to be greater than 0 wherever the function is concave up. That's where it's blue. So for x being from negative infinity to b, and from d to infinity. It's going to be less than 0 in red. So for it to be less than 0, that means it's concave down. The function is concave down, and that happens for x between b and t. And y double prime is going to equal 0 at all the points of inflection. Well, we clearly have these points of inflection already marked on our graph. So points of inflection occur when x equals b and d. So from this graph, just conceptually, we can get a big picture of what's going on with y prime and what's going on with y double prime. And getting more of a kind of a conceptual understanding of y double prime. If we look at this function, distance and time, the first derivative tells us the change in d over the change in t for the velocity. And we were looking at that a lot before. What would the second derivative tell us? The second derivative is the derivative of the derivative. Well, the derivative is velocity. So what we're looking at is the derivative of the derivative. And what's the change in velocity with respect to x? Well, physics students, hopefully you can chime in here. Remember this. The change in velocity, how velocity changes with time, just to hopefully give you sort of a sense of, or an intuitive connection to y prime. This is our acceleration. For some of you, this will be great help. For some of you, it might not be that much help. But for us to think about y being position, y prime being velocity, and y double prime being acceleration. For anyone who studied physics, now I think you can have more of an appreciation for what that second derivative is. Okay, so let's do some math together. We want to, given some function, we're going to be using our calculator for this, for x being greater than -1, we want to find the x coordinates for local max and min, and the points of inflection. So before we get started, we know that to find the local max, that's when our first derivative goes from positive to 0 to negative. So it has a positive slope, a zero slope, and a negative slope. So my function has a local max. It's going to have a local min, where my first derivative goes from being negative to 0 to positive, meaning it has a negative slope, a zero slope, and a positive slope, giving my function a local min. So that's what I'm looking at to find a local min. And to find point of inflection, we know that the second derivative must either go positive 0 negative or negative 0 positive. So how do we do that? Well, it's all using n-deriv on our calculator. So let's pull up our calculator, and we want to look at y equals e to the x over 2 minus ln of x cubed plus 1. And notice that I've sort of been storing, first derivative and second derivative in here, just it makes it easier. And to find the local max or min, I'm just going to be looking at my second derivative. So since I'm just looking at my second derivative, let's turn that, or my first derivative rather, let's turn the first derivative on, let's turn the function off, my second derivative's off. Right now I'm just looking at max and min, so I'm looking for when my first derivative, this one here, y2, I'm looking for when my first derivative is either goes positive 0 negative or negative 0 positive. So we graph it, fix my typo, we graph it. And here's a graph. I need to go back and turn one of the functions off. So let me just turn this y1 off. So I'm graphing just the first derivative, and I want to look when it's 0 and changes directions. A little tough to see there, so let's press zoom 4. And again, we're looking at the domain x being greater than -1. So we've got 3 points where it goes negative, 0, positive, and then it goes positive, 0, negative, and then negative value, 0, positive. So we're going to have 2 mins and 1 max. So let's find those points, and we find those points by pressing second calc. And I'm looking for zeros. So I'm going to go left of the 0, right of the 0, get a point. Let's take a picture. So if we keep going, we want to find the other 0. So second calc, we want to find the 0. And now we want to find this one over here. So we're moving the cursor over, go below it, and we're going to get our second 0. And we can take a picture of that. And finally, we need to get our third 0. So second calc 0. So what we're finding now are the values of x make my first derivative equals 0. And where my first derivative equals 0, that's where I'm going to get a local max or min on my actual function. And take a picture of this. So now let's figure out what all this stuff means. So right here I have a picture of f prime of x, where I'm finding when f prime of x equals 0, because this is going to tell me my local max or min. So if we look at this point here, we went from a negative value to a 0 to a positive value. So this is going to be a min. So we're going to have a min at x equals negative 0.36. Over here, we went from having a positive first derivative to a 0 to a negative first derivative. So we're going to have a max at x equals 0.487. And over here, we went from having a negative value to a positive value. So we're going to have a min at x equals 1.977. So that tells us our mins and maxes, and those are the x coordinates for those. And we could go to the actual graph itself and kind of confirm that. So if we just went and pulled up the graph of our function and just graphed the first y equals, so we're graphing our original function. As we would expect, we have a min at negative 3.64, that's right there. We have a max at 0.487, that's right there. And then we have another min at 1.977, which is right there. And we found those mins and maxes by inspecting the first derivative. The last thing is, or the next thing, or last thing, to find the inflection points. Well, the inflection points, as we said earlier, the inflection points are when the second derivative equals 0, but more than just equals 0, where it goes from positive to 0 to negative, or negative to 0 to positive, where it goes from concave up to concave down, as is the first case, or concave down to concave up. That will give us the points of inflection. So we need to find out when that second derivative is 0 and make sure it changes sign. So let's look at the second derivative. So here we want to graph just the second derivative. Turn that on, press graph. Takes a little bit of time here. So this is our graph of our second derivative. So the same sort of thing that we need to do. Let's find the zeros. So second calc 0, and go to the left of the first 0, go to the right of the first 0, and we're changing directions. We had a positive second. Here our second derivative was positive, 0, negative, so we're going to have a point of inflection there. And it's going to occur when x, I think when x equals 0, but we'll see in a second. So it's not quite x equals 0, but let's take a picture of that. And now we want to find the other point of inflection, so the one that happens right there. So let's press second calc 0, move over, press enter. And here we get our second point of inflection when x equals 1.09. So let's think about what these points of inflection mean in terms of the real graph. Unfortunately, YouTube is going to be cutting us off soon, so we'll come back to this in just 1 second on the next video. Make sure you watch these continuously, because that'll be important for your understanding.